Assalamu alaikum warahmatullahi wabarakatuh. This is Ahmed Hagadi from SEG CAD Solutions. Today, inshallah, we will make a demonstration for AES heat exchanger. We received the mechanical calculation and thermal calculation for this heat exchanger. And now we will know how we can extract the information from the mechanical and thermal reports to use it during using SEG software. Here we have this thermal mechanical calculation, and from here we can figure that the size of this type of heat exchanger is 460 millimeters inside diameter. The position of this heat exchanger is a horizontal equipment, and the type of this heat exchanger is AES. And from this part, from the thermal report, we can figure that the tube number is 130 tubes, the outside diameter of tube, thickness of tube, length of tube, the pitch and the layout angle, and the TEMA class type, the baffle cut, baffle spacing, and number of baffles. Here we have a sketch for the tube arrangement on the tube sheet, and here on the left hand side the dimensions that we will use it during creating this tube bundle. From the mechanical calculation, we can get the main elements from the mechanical report and the nozzles on this model, like we have T1A, T1, T2A, and here the nozzles on this model. Here a list for the materials that used on this model, like for blades, it's SCA 516 grade 70 with a normal condition. And how we can extract the data for each element from the mechanical report. Here on the right hand side we have an image from the mechanical calculation which indicate the cover dimensions, and you can figure easily that the material of this cover is SA 350 LF2 class 1, and the bolt material, here the dimensions of the element. Okay, after reading the mechanical report and the thermal report, we can make a quick sketches for the elements to use it and make the data entry easier. For example, here we have this channel. That channel contains a blind flange, a gasket, another body flange, shell, and another body flange. Here the names of elements on the mechanical report, like channel flange 1, channel gasket 1, channel flange 2. And here it's better to make a sketch like this to indicate the data before using SEG to make things easy. For example, here for the channel flange 1, that's a cross section of the body flange, and here the dimensions that used in the mechanical calculation, which we mention it here, like flange face outside diameter. So we can make it like that on a sketch. Make it easy. It's the same for the material. Here's the gasket dimensions and the material of this gasket. Another for the second the connected flange dimensions and the number of holes, hole diameter, number of holes, the hub dimensions, all of that we can indicate it easily on a rough sketch like that to use it directly in SEG. Now we will proceed. So those are the steps before proceeding with SEG software to use the mechanical and thermal calculation to start your project. Here, let's create a new project. So from this form, after click on a new project, we will make a name for this project, like demo. And from here, we will select the location of the project. So we will create it on the desktop. From here, you will find different modules for equipment. And actually, we will make a heat exchanger. So we will select the heat exchanger module. And this module will give us the ability to create a tube sheets, expansion joints, and make a tube bundle, tube hole arrangement features. So let's select heat exchanger and click on finish. Now SEG will start creating project data. So from here we will figure that we have the an SEG tree. And this tree, if you select the first node, which is the project node, you can define the project information like project number, project name, all of those information. After defining them, you can click on save. Some of those information you can export it to your drawing title block, so you can make a link between those information and your title block easily. Here for the equipment, if you select the equipment node from the tree, you can make a rename for this equipment. For example, we can name it as AZ5. So that's the name of the equipment. And when we select it, you can get that you have the design data of this equipment. So you can define the information of this equipment by double-clicking on the cell and redefine the values. You have here the shell side, the tube side. So you can define the internal design pressure, external design pressure. And if you would like to know more about how you can import the data to the design data form, you can import it from Excel, external Excel sheet, or by filling it. And on our tutorial videos on our channel, you will find more information about this step and how you can deal with the design. Okay, now the second step on the equipment, when you open the setting tab and open the equipment setting, you can define the position of the equipment, like if you would like to make it horizontal, tilted, or vertical. Okay, so you can select the position of the vessel and select the direction of the assembly. That means that if you would like to start your equipment in horizontal case, which is our case now, you can start the assembly from the left direction to the right direction. Okay, or you can flip that to start from right direction to left direction. You can define the delivered blade dimensions, which used to calculate the required number of blades per sheet, and define the used units during importing data in millimeter or in inches. Okay, now let's start creating the first element, which is in our case, which is the blind flange. Okay, this blind flange. So from here, let's open elements, and from cover, let's add flange 1. Okay, and from here you will find the list of different type of flanges. For our case, we will select the first type, which is exchanger blind flange, and let's define the dimensions of this blind flange. Okay, and the outside diameter of this flange, the thickness of this blind, the bolt circle diameter, the bolt hole diameter, it's 30 millimeters, number of bolts 20, raised face thickness, and the second raised face thickness. The raised face diameter, it's 532, so here it's 532, and the material we can get directly like that and import the material here. Okay.
Can I interrupt in between? Yeah.
Go ahead.
can we extract directly from the PVLAT file to this, or do we need to
for pressure vessels
put
only?
every dimension?
I think maybe Debic inform you about that. For the pressure vessels and towers, we can do that because there is enough information about the equipment to proceed that on the exported access database. But for the heat exchanger, we asked many times Hexagon BBM to make information regarding the tube sheet, flanges, type of flanges of heat exchanger on the report, but the access database file does not include those information. So we, for heat exchanger, we should create it like that. And you, during this session, you will figure out how much time we can take. I think it's not more time, and it's easier to make it by using the features of SEG. Okay, we will make it 4 passes. Define the and here's the part. Okay, and here the bar offset. And let's click on save. Now let's create the first part, which is the blind, the cover flange. Here, as you can see, SEG creating the part on behind. And if you would like to make a rendering for the element during creation and make a rendering for childs during creation, we can select a setting here from the app setting, which is child preview and parent preview. And when you click save, now if you create any part, it will be rendered during creation. Let's try this. Here, let's add a gasket. So from elements, let's add a gasket with a pass partition. So from here, let's add channel G1. Is the first gasket on this channel. Select the number of passes here, 4 passes, and the gasket for the front side, like that. And from here, let's define the inner diameter of the gasket, and the gasket thickness, and the gasket width according to the calculation, and the gasket offset. And let's define the gasket material. Here we have this material, and let's define it like that and click on save. Now let's click start assembly. Now, as you can figure, the I should have add a dot here and click on. Okay, so we have this gasket, okay, of the for this cover. Now let's add the next element, which is this flange.
For this gasket, the pass partition is. Can we change it to double jacketer, or do we have any option for that, or it's a single piece of spiral?
It's like that, but if you would like to make a separate detail, you can make that, and if you would like to edit on this gasket, you can do that. Okay, but
because the outer will be spiral one and the rib will be double jacketed.
I see. As I informed you that that type is the available types on SEG, and if you would like to make a separate detail inside the drawing, you can do that.
Okay. And in our case, the channel is on cladded and overlay.
I know.
So,
I know. We will keep this at that. Okay, because in the mechanical calculation, it's not appear, and I will show you that the dimensions on the mechanical calculation need to be modified, because after adding the clad, the raised faces diameter and the inside diameter of flanges will need to be modified.
That's it.
Because in the mechanical calculation, it's okay, but after making the 3D model and the drawing, you will figure that you have an intersect, or interference between the clad and the raised faces of flanges. So after creating the 3D model, we will add the clad and modify the dimensions. After that, you can reflect that on your mechanical calculation again and thermal calculation. But keep steps as it is right now to show you step by step how we can create.
Yeah, fine.
Okay. So we will proceed with creating the next flange, which is a body flange. So from here, you will find the standard flanges, but in our case here with this heat exchanger, we will use a designed flange. Okay, for the designed flanges, we will have this type, which is channel flange 2. And from this list, as you can figure, the first type with a raised face like that. But in our case, we need it with a grooved face. So if you take a look to the image on the right-hand side, we need to make a groove for this raised face. So we will select the next type, which is integral weld neck grooved face, and define the inside diameter. Here, that's the carbon steel inside diameter, not the cladded diameter. So it's 466. And from here, let's define the end thickness, which is 10 millimeters. The neck thickness.
Yeah, Ahmad, can you enlarge the screen so that it will be
please
readable? Enlarge the screen is possible because cannot read the dimensions.
I think you can make that from your side, not from my side. You can make a stretch for the screen from your side or increase the view, but from my side, I cannot do that. Okay, the flange outside diameter 645, and the flange thickness is 70 millimeters. The raised face thickness is 5 millimeters. The raised face outside diameter is 535, and from here the bolt circle diameter is 575 millimeters. The bolt hole diameter is 30 millimeters. The number of bolts is 20, and the material we can get it here and directly import it like that, and make this flange direction is flipped. Okay, but let's create it without making a flip to figure out the default direction, how it comes. Okay, here now this flange will be created. And if we take a look from the right-hand side and make a section, let's make a section here to show you why we need to make a flip. So the direction of this flange, you can figure that the raised face is in this side. So we need to make a flip to flip the direction of the flange. So from here, let's flip the flange direction and change the flange direction to make the facing to the gasket direction. Here we have this gasket. Here we have this connection like this. Okay, the cover gasket and the body flange. Now let's add a channel. So from here, it's channel 10. And here from this can, let's select shell type, define the inside diameter, the thickness, the longitudinal welding line orientation, and the length of this can, the weld gap, the material of this can. Let's add another element, which is another body flange. So from design the flanges, let's add channel flange 3, and let's make it looks like channel flange 2 because they are the same dimension, but one of them is flipped, takes the other direction. So let's click on save, and from here we will remove flip from this side. Let's add another gasket. So from here, let's add channel gasket 2, and let's make it looks like channel gasket 1 because they are the same. They are facing the pass partition and the groove on the tube sheet. So let's click on add. So if you select this channel, automatically you can figure that the type of passes automatically selected as 4 passes, the same dimensions of the previous channel, previous gasket. Now let's click on start. Now we have this channel, the second flange, and the last gasket. Okay, now we have the channel without nozzles or pass partition or clad, but go on and create the tube sheet. So from here, let's create the tube sheet. So let's add the next element, which is tube sheet. So from here, let's add tube sheet. Okay, and as per the mechanical calculation, it's extended as a flange. Okay, so let's select the type of tube sheet gasketed with shell and the channel extended as a flange. So that's our type. Define the outside diameter of as per the image on the right hand side here. That's the outside diameter, and the left inside diameter. Right. The resin face thicknesses and the thickness of the tube sheet as per the mechanical calculation. The resin face diameter, and here the resin face thicknesses. Here the bolt circle diameter and bolt hole diameter 30 millimeters. The number of holes is 20, and here the material of this tube sheet. Here let's add a tube passes. So from here let's select 4 passes and define the offset of this tube path, and let's click on save, and let's create this tube sheet. Here, okay, here we have this tube sheet with a groove like that here. So let's make a tube holing arrangement for this tube sheet and proceed with the tube bundle arrangement. So from here, let's come back to the tube sheet, and from tube sheet bundle, let's make a new model and define the inside diameter of this tube sheet. Define the thickness, the tube side diameter. So let's come back here. It's here's the tube clearance, okay, and the top clearance. And for the tube passes, let's select 4 passes. Define the pass lane width. So from here it's like that, and that option will give you the ability, if you move one of pass partitions, the symmetric one will move the same like that one. From here, let's define the tie rod diameter, the tie rod hole diameter, the same for the sealing rod and the tubes, and let's keep those options as they are, because here in our case, if you select this hole, for example, to convert it to a tie rod, the symmetric one will be converted. So we will not select those options. And here, that's the tube layout. And from here, let's select the tube layout. It's 45, the big point, and let's start drawing like that. And from the pass partition, we will move the pass partition a little bit down. So we have this pass partition like that, and the number of holes per room, it's not the same. So let's come back to here and change this little bit, and from the pass lanes, let's minimize the number of holes like that. It's not the same. We need 31 holes here, 31 holes for this room. So from here, we can come back here and change the clearance from the sides, and from the pass partition, let's move that down like that. As you can figure, we have 32 holes on this room and another 32 holes on this room, and we need to decrease the number of holes from top and bottom. So let's come back here and this one like that, and click draw, and let's move the pass partitions like that. And we could start from here, or we can increase the height at the top and bottom. So let's move it, and let's try now. So from pass partitions, we can move the pass partitions like that. Okay. So from here, we can convert this hole to a tie rod, and the same for that one on that side. Okay, we can remove this hole, so we can remove both of those like that. So we can remove them to make a ceiling bar. So we will remove those holes, make that one as a tie rod, and another tie rod. Okay, so we can apply those changes and export them. Now this arrangement is successfully saved. Now we can add a tube to this model. So from here, from elements, let's add a tube to this model. So from here, let's add a tube. From here, the first type of tubes include a standard lengths of tubes as per EMA, but in our case, it's user-defined length. Here, that's the length of the tube. Here, that's the length of the tube. So we will define this value here. And the thickness of the tube, it's like that. So we can directly. And the material of the tube, it's that one. So we can like this. And the offset from the tube sheet is 3 millimeters. Now let's add a tie rod. Okay, so let's add a tie rod from here. So okay, and let's click on save. Okay, from here, let's define the dimensions of this tie rod. Let's keep those dimensions as they are, but from here, let's define the material of this tie rod and the nut material, 7M. Okay, and let's click on save. After that, we will modify the tie rod length after creating the baffle. The baffles. After that, we will measure the value from the model and reflect it on the item here. Now we have this tie rod. Let's add the first baffle. Okay, we have a segmental baffle. Let's define the inside diameter of the element of the shell side, the baffle height, okay, and the spacing between baffles. For the symmetrical baffles, if we take a look to the mechanical calculation here, for the symmetrical baffle for this one and the second one, it's double this value, which is spacing 300. So it will be 600. So it will be 600, and the thickness will be 8 millimeters clearance. The material of the baffle, the location of the first baffle, the orientation will be on 190 degrees. So the cut here, the cut will be at the bottom, so it will be on 190 degrees. Now let's add a vent, the vent height, and the number of baffles is 9. And click on save. So if you come here and calculate the number of baffles or symmetrical baffles, it's 9. So click save. And now let's add another baffle, baffle 2, and let's make it looks like baffle 1. But here we will make some changes. The first change is the orientation, so the cut will be at the top. So we will change this and change the location of the first baffle. Here, the first baffle here equals the spacing, which is 300, and the first baffle location. So this value will be like that. And let's remove the vent and keep the number of baffles as it is. Now let's define the second, the last baffle, which is the end baffle. So from here, let's add baffle. From the end baffle here, let's select the end baffle and define the side diameter. Cut on the middle, the thickness of this baffle, the clearance, the material, and the location of the baffle, the orientation, spacing, no spacing, cut, and chamfer. And let's click on save. Now let's create those items. The last part, let's add the floating head. We have a floating head on this one. So from here, let's add floating head. And from the floating head, let's define the floating head dimensions as per the dimensions mentioned on the image on the right hand side. So from here, let's define the outside diameter of the tube sheet. The left pressed face. Sorry. The left face width, the thickness of the tube sheet is 60 millimeters. The material of the tube sheet. The tube length, the tube extension, the backing ring OD, the backing ring. Let's keep those default dimensions. The bolt circle diameter. The hole diameter is 22 millimeters. The number of holes is 24. Backing ring material, split thickness, split width, number of holes per split. Okay, the gasket thickness. The gasket inside diameter, the gasket width, and the gasket material. So it's gasket material. Here, those dimensions will keep them. The floating head material. That's the spherical portion thickness. It's 8.5, and for the radius 325, and here it's normalized. And for the lug thickness, let's keep those dimensions for the lifting lug material, and the size of the bolt. It's 20 millimeters, and the stud length. Here's the material of the nut, 7M.
Yeah, Ahmad, for this, if we don't want the splice, then we can avoid it.
We have what?
If splice is not required, then we can put the dimension of 0.
You would like to remove the split plate.
Yeah, splice. Yeah.
Okay, in this type, it's not possible. But if you have a request like this, our technical team can do that, because one of our clients asked us to make an option here for this split, to make it threaded, to make the split threaded. So no need to use a nuts on the after the split. So if you have a request like that, you can raise it to our technical team or our development team, so we can make it easily, inshallah. Don't worry about that. The updating and making requests, it's for free for our clients.
Okay.
Okay. Here we have this floating head. After creating this floating head, we will proceed with creating the items. So here we will, as you can see, we add a tube, tie rod, and 3 different baffles and floating head. Here SEG will proceed with creating those elements. The second baffle. The floating head items, the first item, which is the tube sheet, the backing ring, Okay, now after creating the floating head, now we have this tube bundle, but without patterning the tubes or making the holes. One more thing we need to modify, which is the tie rod length. So from here, let's measure the required length. So from here, let's measure the distance from the last baffle, or we could change the location of this last baffle a little bit. So from here, let's come to the end baffle and change the location. Make update. Okay, we could minimize this value a little bit with 50 millimeters and update. Okay, now let's measure the required length, the actual required length for the tie rod. So here's the value. So 854. So we will increase that one. 854 and click on save. Now let's start updating the tie rod. Okay, now let's start patterning the item. So from here, let's come back to the tube sheet. And from here, from tube sheet holing, we will proceed with creating the holes. Here, you can figure that the location of each hole in X and Y direction on this list. So from here, let's click on start holing. Sorry. Here, if you take a look during creation, SEG start creating a location of holes for the each tube sheet and for holes of tubes like that, and make a pattern for it. The same for the baffles. Okay, now we finish the arrangement of the holing of the this one. So let's make it whole section. So we have the tubes and tie rods on the 3D model. Now let's complete the model of this heat exchanger, and after that, let's add the attachments like nozzles, bus partitions, all of that. So from here, let's come back to the SEG application, and let's add a gasket here. After, as you can figure after the tube sheet, we have another gasket, but not a gasket with bus partition. It's a ring gasket. So from here, let's add channel gasket 1. So from here, let's define the gasket inside diameter and the width of this gasket, the material of the gasket. Save. Now let's add a body flange. So let's select designed body flange. So from here, let's add channel flange 1. And we could make it looks like a channel flange 2, and we can modify some of those dimensions like the inside diameter, because the inside diameter of this flange is a little bit different because it's without clad. For the clad on the channel only, not on the shell side. The end thickness is 12, not 10. The neck thickness, and for the flange OD, it's the same. The flange thickness is 75. The raised face the same. Raised face outside diameter, it's the same. The bolt circle diameter, the other data are the same. Now let's click on Start Assembly to create the gasket and the body flange. So if we take a half section on this model and take a look here, that's the tube sheet with the 2 flanges connection like that. And I think from on that side, we need to minimize the raised face diameter, okay, to make a clearance at least 1.5 millimeters from the inside diameter of the shell. So things like that, we can modify it in one time after adding a clad on this side, because after adding a clad here, we need to decrease the raised face diameter here, and the same on that side. After adding a clad here, we will need to decrease the raised face diameter on that side. So let's complete creating the model. Let's come back here, and from here let's select can. So it's shell side can 1, and let's select shell type, define the inside diameter, thickness, the longitudinal building line orientation, the length, and the material of this can. Click save. Let's add another can, because the total length of this can, it's 5,650. So let's add another can, shell can 2. Let's make it looks like shell can 1, but we will make some modifications. So from here, let's define the longitudinal building line orientation, define the length, and click on save. Let's add another can, which is can 3. So shell can 3, and make it looks like shell can 1. Click add, and keep the dimensions as it is, the longitudinal building line orientation, the length, and everything. So the total length for 3 shells will give us the total length of the length as per the mechanical calculation. Now let's add another flange. So from here, let's add another designed flange, which is shell flange 2. And when we select this type, you can figure that we need to make it with a raised face, not a grooved face. So we need to make this type. So we will select the first type here, which is integral weld neck with a raised face. Let's define the inside diameter, the end thickness, the neck thickness, the neck length, the flange outside diameter, and here's the flange thickness, 75, and the raised face thickness, the raised face outside diameter, the bolt circle diameter, and the number of bolts. We have the bolt hole diameter is 30 millimeters, and they are 24 bolts, and the material of this flange will be like that. And let's click on save. Now if we click run for the assembly, we will proceed with generating 3 shell courses and a body flange. So let's generate them one time to check if we have any interference between the body flange and floating head or not. So I think it's okay, and the last partition location is okay. It's laid on the body flange here, so it's okay. All right, now let's add the second or the gasket and the bonnet items. So from here, let's come to here, and let's add a gasket. It's a sim ring gasket, not a gasket with pass partition. So let's channel G2, gasket number 2, and let's make it looks like channel gasket 1, but we will change the inside diameter. So the inside diameter here is different. The thickness and width, they are the same. And now let's add another flange, which is channel flange 3, and let's click on save. For this type of flange, we will select integral weld neck with a grooved face, which is the type. Define the inside diameter, which is 545, and the end thickness is 10 millimeters. And the flange outside diameter. The flange the flange thickness is 80 millimeters. the raised face thickness is 5, and the raised face outside diameter. Here's a bolt circle diameter. So the bolt circle diameter is 6.5, and from here the hole diameter is 30 millimeters. The number of bolts is 24, and the material this one like that. And let's make this flange as a flipped flange. Now let's add another can, which is bonnet. Okay, so here let's select a shell, define the inside diameter of of this one as 545, the thickness 10 millimeters, the longitudinal building line orientation, and the length is 300 millimeters. The material, and let's click on save. Let's add the last element, which is bonnet. Define the inside diameter. Select. You can figure that you have many different types, more than 17 different types of head, like hemispherical head with negative straight flange, conical head, many different types. You will find it in this list. So let's select ellipsoidal head as a half of ellipse. And if you would like to make it with crown and knuckle radius, you can select easily select ellipsoidal head with crown and knuckle radius. And if you would like to modify the crown and knuckle radius, it's not a standard type, and you would like to modify the crown and knuckle radius, you can select user define the crown and knuckle radius. Here, let's select ellipsoidal head and define the inside diameter. Right, the thickness, the straight flange length. The thickness is 11, and the minimum thickness after forming is 10. And here, that's the material of this head. And let's make it as a flipped head. Now, let's create the final main elements of the heat exchanger. I think the bolt circle diameter, it's not defined correctly on the body flange. So let's come back here to channel flange, and let's check the bolt circle diameter. So the bolt circle diameter is 655. We need to modify this value because if we come back here and check this value, you can figure that the bolt circle diameter is not the same on the other flange. So after modifying it, making it like that value, we can update the model. So the bolt circle diameter of this flange will be modified like that. Now we have the main elements of the heat exchanger. The next step, we will generate or create the nozzles on this model, and after that we can add the supports, bus partitions, lifting lugs, a nameplate, and add some other attachments. After that we can proceed with the mechanical drawings. Okay, from here let's select can 1, and from elements let's add a nozzle which is T1A. And from here, let's select this nozzle from the tree, and you can figure that you have many different types of nozzles, like a nozzle from pipe, nozzle from plate, connected nozzle, tangent nozzle, long weld neck nozzle with raised face flange, long weld neck nozzle with RTJ facing. Self-reinforcement nozzle with lips, many different types you can select with them. In our case here, we have a long weld neck with RTJ facing. So from here, let's select this type and select the rating of this flange, select the size, and define the location, the orientation, define the material of this element, define the service of this nozzle as an inlet nozzle, and let's click on save. Now from the calculator we can define the projection from the facing of this nozzle to the center line of the vessel, which is 5 to 5, and let's click on calculate and click on save. Now the projection automatically defined it. Now let's define the set weld. In our case, we have the thickness is not great, so we can make it as a single V. But if you would like to make it a double V, you can select the welding detail like that. Here, if you would like to make a detail of the welding without clad, or without clad on the parent element only, or a clad on the parent and nozzle from the inside, and you have a weld overlay like that. Now let's define the weld fillet, which is a dimension like that. So we have T1A. Let's add another nozzle, which is T1B. Okay, and let's make it looks like T1A. So let's select it from here and let's make it looks like T1A. But we will make a small modification here by modifying the orientation of this nozzle to make it on 0 degree and define the name of this nozzle as outlet. It's outlet nozzle. Let's click on save. Now if we click on start assembly, here we have those nozzles T1A and T1B with a ring joint facing like that. Let's add the channel nozzles and bonnet. So from here, let's select can 1 from the shell side, and from elements, let's add nozzles. So S1A, that's the first nozzle. And from here, let's select long weld neck with RTJ and define the rating, select the size, define the location of this nozzle, the orientation, the material. And for the projection, let's keep it as it is until calculation. And from here, it's inlet nozzle. Okay, so let's save this. And from the calculator, let's define the projection from the vessel center line. So from the vessel center line, as per the mechanical calculation, the projection is 670. And I don't know why you make this projection is different from the other nozzles, but it's with that value, which is 428 millimeters from the outside diameter of the shell. But okay, I keep it like in the mechanical calculation, and let's click on save. And from the set weld, we will select parent nozzle clad, define the fillet weld, and click save. Now let's add another nozzle, which is S1B. Okay, and let's click on save. And we will make it looks like S1A. But we will make a change with the orientation and location because they are the same. So the location will be at 5,480 and the orientation 180 degrees, and the service of this nozzle as outlet nozzle. And let's click on save. Now let's add nozzles on the bonnet can. So from here, let's select bonnet can, and from here, let's add V1, which is a vent nozzle. And let's select the vent nozzle from here and select RTJ long weld neck. It's 2 inches. Define the location, the orientation at 0 degree. The material of this nozzle, it's vent nozzle. And let's click on save. And from the calculator, let's define the projection. It's 540. Click calculate. That's the projection from the here. That's the projection from the shell outside diameter. So automatically it will be reflected here. And let's find the set weld. It's 9 millimeters. And click Save. Now let's add another nozzle, which is drain nozzle. So it's B1. And we will make it looks like B1. Okay. Refresh the node and come back here. Define the orientation 180 degrees. It's drain nozzle, and let's click Save. Now we have the nozzles of the model. The inlet and outlet nozzle, and the vent and the drain nozzle on the bonnet. Okay, now we have those nozzles. As you can figure, this nozzle projection, I defined it as per the mechanical calculation. That may be for some reason, but that's the shape of this nozzle. If we take a section, half section on the model to figure out the nozzle locations, here it's before the first baffle, and here before after the last baffle, between the last baffle and end baffle. Okay, and here the end baffle location, the tube bundle, and we can figure easily that we have a clearance for thermal expansion of the floating head and enough area after that one. Okay, now let's add some other attachments like the pass partition on the channel. So let's select this channel, and from internal attachments, let's add a front pass partition. As you can figure, when you select the main element, you will get a list of attachments you can add it to this element. For example, here, when we select the shell, you can find a list of supports like adding saddle, tilted saddle, stacked saddle, leg, lugs, skirt, anchor chair, different type of cradles. Suits the small sizes of vessels like a receiver, small receivers, and like that. All of those type of cradles, we create them as per one of our clients' request. They are a manufacturer of air receivers in UK. So those types may help other manufacturers. Okay, here a list of nozzles like a nozzle with external connection, a nozzles with internal and external connection. So if you have a nozzle with internal projection and you would like to make internal piping inside the vessel, you can do that easily. Coupling, clean outdoors, weld outlet, stud outlet couplings, a list of different type of lifting lugs. So you will find here different types of lifting lugs and the trunnions. External attachments like adding nameplates, grounding lug, Bob David, many different type of attachments, external attachments, and a list of internal attachments like the one of them is internal pass partition, internal rungs, impingement baffles, deflectors, bundle retainer, clad, all of that. So from here, in our case, we will add a front pass partition to this shell. So pass. Let's add a pass partition. So from this pass partition, we will select 4 passes like that. Define the thickness, the end thickness, the lift extension, which is on the flange, right and left flange, the chamfer, the pinhole diameter, the pass partition material, the orientation, and the offset of the pass partition, and let's click on save. Now let's read this pass partition. Sorry. Let's take a half section here. So here, if you take a look, here we have this pass partition with chamfered end or tilted end like that to suit the gasket, and the same on the other side here for the tube on the tube sheet side. And the extension length, which is mentioned here, which is left extension and right extension, which is the distance from the end of the shell to the facing of to the gasket here on this side. Okay, now let's add support baffles, and let's add some other attachments like sealing bars, here. And if we would like to add sliding bars at the bottom, we can do that, and we will discuss how we can make it and how we can add spacers to the tube bundle. Okay, so let's add saddles. So from here, let's select can 1 on the shell side. Okay, so you should select the suitable main item for that. So we need to add a saddle on this can, on that one. So we will select it from the SEG tree, and from elements, let's add a saddle. So let's add the left saddle and select it from the tree. And you can figure that you have 12 different types of saddles. Let's select the first type, and we could discuss on another PowerPoint slides the different types of saddles and the lifting lugs as a sample and the different type of nozzles. But let's create the our model first and generate the drawings. After that, we can discuss the different configurations and the types for some items. So from here, let's select the left saddle and define the saddle contact angle, the saddle height as per the mechanical calculation, the width thickness. Let's add a wear blade, find the width and the thickness of the wear blade. Here, that's the material of the wear blade. The base blade dimensions, 170, the thickness of base blade. Here's the hole diameter and the hole location and the base plate material. From here, that's the web material, and we have an outer ribs with 150. Here the width is 14 millimeters thickness. Material of the web. We have a mid rib, so let's activate the mid rib and click on save. The location of the first saddle. There's a mechanical calculation, and now let's create this saddle. Okay, so we can move the holes a little bit to the center of the base plate. So the offset from the long direction can be changed. So here the offset from the long direction could be the half of this value. So the offset from here be like that. Or we could make it as a 4 holes if you would like to make a second row. So, for example, if we change it like that and make the hole 30 millimeters and click on save, and if you click on run, the hole dimensions will be changed like that. So after creating the 3D model, you can make some customization, like if you would like to decrease the base plate length and make the holes to the inside. So the 3D model will guide you if you would like to make a modification on your mechanical calculation. So that's the mechanical calculation information. After reflecting it on the 3D model, you can figure that for fabrication wise or something like that, you will need to make a modification again in your mechanical calculations to suit the fabrication requirement. Now let's add the second saddle. So from here, let's select pan 1, and let's add another saddle, which is the right saddle. And let's make it looks like the first saddle, which is left saddle, because they are the same dimensions, but one of them will be with slot holes and with a different location. So we will make it looks like the left saddle, and let's click on add. But when we select it, we will change the location of this saddle and make it with slot holes like that. And let's click on save. So we have the same saddle dimensions, but on another location and with slot holes. Okay, as you can see, you can make this saddle with slot holes like that. And with the different type of saddles, let's check one more thing. Regarding the available types of saddles and the options. Here, if we take a look to the different types of saddles, you can make this saddle with a straight web without any edges here. Let's, as you can figure, the web here not include any straight edges like that. Here we have a straight edge perpendicular to the base plate, and that one is to the center of the vessel. Okay, but that type not include that shape. Another type with a lifting lug. So for the first type, you have 3 different cases. You can make the web at the left, at the middle, or at the right side. You can control the bottom width of the web, so you can make this web with straight sides. You can make it with a narrow width like that, or a wide width with wide bottom width like that. The same options for the other types of saddle. Here you have a straight edge here. Goes to the center of the vessel. The same options you can make the web or at the left, right, or at the middle. You can control the bottom width of the web, and you can make the web with straight sides like that. The same for this type with straight edges perpendicular to the base plate. Finally, the last type with lifting lugs like that. Another options for the hauling and reps. Here, if you, in some specs, you may need to make a cut here because you haven't enough area to tight the nut. So some specs include this cut on the web to give you the ability, if you have a single bolt here on the middle, so you need to make a cut to get enough area to tight this bolt. You can make the arrangement of holes on the short direction like that, or make it on the long direction. You can make the base plate with straight holes or slot holes, or make it without any holes. In some specs, the sliding saddle not include any holes, and it's fixed from the outside by, let's say, a flipped flange or another device with a Teflon below the base plate to make it sliding without using any anchor bolts. You can add stiffening grips up to 9 grips. Here for the lifting lugs, in SEG software, you will find many different types of lifting lugs, suits the different cases for horizontal, vertical, small sizes, large sizes, and mid sizes, trunnions and many other shapes. Here, a quick look for the different types available in SEG and the different dimensions that you will need to modify during importing for small sizes and mid sizes, larger sizes. For this type of cross lifting glove, if you will lift from a single point, you will need to make this type of lifting lug, which is cross type. A suitable type for shifted lifting lug. If you have a body flange, for example, and you would like to make a lifting lug slightly offset from the outside diameter of the body flange, you can use this type of lifting lug, or use a trunnion, for example, or this type of lifting lug. For the different type of nozzles, if we take a look to the different type of nozzles here. In SEG software, you will find many different types of nozzles, like nozzle from pipe, from blade, long weld neck nozzles according to ASME or European codes, long weld neck with lips, forged hub with lips, integral hub with lips, rectangular opening, and oval opening. We have more than 23 types available on the shell, and those are most common types. Different types of supports, like saddles. As we mentioned, the saddle include 11 types of saddles, different type of saddles, stacked saddle, tilted saddle, skirt. All of those types, each type of those include other types. Okay, let's come back to our model. Here we have this support saddle. Now let's add the lifting lugs for the channel and bonnet. So from here, let's select the channel and define the lifting lugs as per the mechanical calculation. So from here, let's select the suitable type as per mechanical calculation, which is type 2 here in SEG. And let's add lug 1. And from here, let's define the width and the offset, which is dimension D, the offset E, the thickness. This length, the radius is 75. The pinhole diameter, the material of the lifting lug, the location and orientation, it's on 45 degrees. And let's click on save, and let's create this lifting lug. So after creating this lifting lug, you can figure easily this lifting lug is a little bit huge comparing with the size of the channel. So we can minimize it. And it's laid on the welding line, so we can change the welding line orientation and change the dimensions of this lifting lug a little bit. So before that, you should check your mechanical calculation before changing that. But let's change it to show you how we can make that easily. So let's define this one, the radius, and let's keep this one as it is, and let's click on save to change the lifting lug dimensions to make it little bit make sense. Here I think it's the configuration of the lifting lug is it's okay. And if you would like to add a wear plate to this one, you can add a wear plate like that. So let's define the dimension A. So let's check the image on the right hand side. So that's dimension A. Let's make it 50 millimeters. Dimension B. So let's make it a little bit greater than this value. The thickness is 10 millimeters. The fillet and one. So the location, keep it as it is. And from here, let's click on start simply to modify the lifting lug by adding a wear plate to lifting lug. You can add a cooler. Now let's change the longitudinal welding line orientation. So from here, we can change the orientation of the longitudinal welding line little bit. So let's make it on 80 degrees, and let's click start the assembly. Okay, so I think it's far from the lifting lug location. And if we take a half section from here, let's take a half section like that. So I think it's far from the, not from here. Let's take it from that side. Okay, to check if it's near from the bus partition or not. And if you would like to measure the distance between this welding line and the bus partition, you can easily measure the distance from here to there. It's 26 millimeters. I think after adding welding and clad, it will not be okay. So we can increase this value, or change the orientation of this welding line here to increase the clearance between welding lines here and there. Okay, but right now let's keep it as it is. One more thing we would like to check here for the shackle option, or how we can check if this pinhole suits the shackle size or not. Here, if we open the new items, you will find a library for SEG. Here it's SEG items library, and on this library you will find a crossbee shackle. So if you would like to use one of those shackles, standard shackles according to crossbee shackles, you can select it from the list and modify the size or the load of this shackle. For example, let's use a shackle with 3 tons and 250 kilograms. So that's the shackle, and here that's the bin diameter, for example. And let's save this shackle. So from here, let's save this document and come back here. Okay, so let's import this shackle here. So from simply, let's import this shackle and check if this shackle will suits this lifting lug or not. Is there any enough area for the wire or not? Here, after adding this, for example, if we take a look, no enough area, so we can increase this offset a bit. So millimeters or millimeters like that. You can figure that by visual inspection here. Not enough area for the wire here, so we could use another shackle. So if we come back here and increase the shackle, let's make it 8 tons, for example. So the rod diameter will increase. And if we come back here and make an update, you can easily figure that the pinhole diameter suits the bin diameter, and here you have enough area for the wire or slings to lift this one. Okay, so that's one of a quick checks you can make it by using the SEG tools during generation of this model. Now let's add the second lifting lug on the other side, and let's add another lifting lugs on the bonnet. So from here, let's select the shell and let's add another lifting lug, 2, and let's make it looks like lug 1, but we will change the orientation of this one and click save. On the bonnet, we will make the same thing. Let's add another channel, another lifting lug, lug 3. Okay, and we could make this lifting lug looks like lug 1, and let's click on save. Okay, but let's change the location of this one to make it on 150. Let's click save. let's add another lug, which is lug 4, and let's make it looks like lug 3, but we will change the orientation of this one. That, and let's click on create assembly. Here, as you can figure, we have the same interference between the longitudinal building line on the bonnet and the lifting lug. As we discussed, you can go back to the bonnet can and change the longitudinal building line orientation and modify it. So the longitudinal building line orientation will be modified like that to be cleared from the from the welding line. Now let's add sealing bars on the shell, on the bundle arrangement. So we need to add sliding bars here. Okay, so from here let's select the channel tube sheet, and from here let's select sealing bars. Okay. From here you can make a single bar or a double vertical bars like that. So we can this time define the inside diameter of the shell. The thickness will be 8 millimeters. The clearance will be 0, and the length of this one will be like that, and the height of this one, as per sketch here, it's dimension h, and define the dimension of this one. The location will be at 0 degree, and the orientation will be on like that, and the spacing between those two items will be like that. And let's click on save. Now let's click on the simply to generate the sealing bars. Okay, so we have those sealing bars here on the central line of the nozzle. Now we need to add another sealing bars on the other side. So we will add another sealing bar. So from here, from elements, let's add sealing bar 2. And let's make it look like sealing bar 1. But we will change the orientation like that. And let's start the assembly. Okay, now we have another sealing bars here. Now let's make one more thing, like adding a nameplate and earthing lug for this exchanger, adding tightening bolts for the flanges. After that, we will proceed with cladding inside the channel and how we can deal with that. Inshallah, after that, we will proceed with drawing creation. Okay, now let's come back here and add a nameplate. So let's select channel CAN 1, and from here let's select external attachments and select nameplate. So let's add a nameplate, and from here let's define the suitable type for the nameplate. Here you have many different types of nameplates, and from here let's select vertical bracket for a single support. Let's define the length, width, thickness, projection, and the material, the location, orientation, the material of the support bracket, support width, same. Let's keep those dimensions as they are. Let's add an ASME nameplate bracket and the client nameplate bracket. And this to be like that, and click on save. Let's add an earthing lug. So from here, let's add a grounding lug. So let's select a grounding lug. Sorry, you will find many different types of lifting grounding lugs. Let's select the second type and keep the dimensions as they are. Define the location, click on save, and generate the 3D model. Okay, now you can figure that the location of this earthing lug not located on the saddle, because in SEG software we dealing with the attachments to be available only for the main elements. So you can add the attachment to the main element. So how we can move this earthing lug from the main element to the saddle on the 3D model? It's easy. Now let's open the earthing lug, and here that's the default constraints from SEG. We will delete them, and now let's add manual constraints for this element. So let's select this one and add it here, and make it flush with this surface with 2 millimeters, and from here to there, let's make it make the offset 100 millimeters, or let's increase it a little bit. Okay, so we have this earthing lug now here on the support saddle. Okay, I think now we generate the 3D model. One more thing we will proceed it, create it before generating the cladding on the shell side, which is make a nozzle holing. If we take a half section here and make a cut here, you can figure that on the shell side, no cut for nozzles here. So if you open the shell, for example, if we open this shell and make a sheet metal flat pattern, you can get a sheet metal flat pattern for this sheet plate. It's not include any holing. So how to make a cut holing by using SEG software? That's one more step we will make it here. From opening, let's open the this form, and from here let's load the nozzles on this model. Now we have all of those nozzles created on the heat exchanger. You can figure that we have T1A, T1B, S1A, S1B, D1, and D1. One more thing here, I will make it here for the nozzle, this nozzle, which is nozzle S1B. It's in SEG, it's located on CAN 1. Okay, you can figure that it's located on CAN 1. If you take a look to the tree, SEG tree, you can figure that S1B, it's located on CAN 1. But it's in real, it's located on the third CAN. We have another CAN here. So it's located on the third CAN. So we can neglect it from this analyze, and we will make it with another analyze, which is analyze interference. There is a tutorial video discussing that in deep, give you the different options for holing. So here we can make a cut with cut clearance with 2 millimeters, and let's extrude cut to create a cut for those nozzles, except nozzle in S1B, and we will generate the whole of this nozzle separately by the same tool, but with another option, which is analyze interference, because this option will give you the ability to detect which is the real item which is located for this nozzle. Okay, here you can figure that we make a nozzle cut hole here for those nozzles with a clearance with 2 millimeters cut clearance. So for this nozzle here, we need to make a cut for this. Okay, now let's close this form and open it again. And now let's load all nozzles. Let's remove all nozzles, but right now let's select S1B, and we will make an option here for the which is analyze interference. Analyze interference, this option will give you the ability to detect where this nozzle is located, actually located. It's not located on the parent item. Here we add it on SEG on CAN1, but actually it's located on, it's intersected with CAN3. So here SEG automatically will detect that. So by making this option, which is analyze interference, which is, it takes a little bit time more than the other option. This option will give us the ability to detect the actual main element. Okay, so automatically it's detected that element and create a hole on this element. Okay, that's another option for holing. Okay, now let's collapse all childs like that. Now we have this element. Now let's add a clad to the shell side and detect the how much modifications we need to do after adding the cladding to the shell, to the channel side. So from here, let's select the channel, and from elements, let's add an internal attachment like clad. So it's a channel add. And from here, you have two different options. If you would like to include the clad as a separate part on the bill of material, okay, because it may be supplied as a separate sheet, and by another way you will weld it to the shell, or it's not included in the bill of material as a separate part. In this case, we will not include it in the bill of material as a separate part. Define the clad thickness and get the clad material from here. So that's the clad material and the density of this clad. And let's click on save. Now let's create a clad on the shell. So we have a clad on this shell like that. And let's add a clad on flange number 3 here, channel flange number 3. Let's add a clad and make a facing with a clad for this one. So let's open this flange, and by using a technique here, we can make a split for this item like that. So we make two different items. So from here, let's make it as a copper polished like that. And let's add a cladding at the inside. So from here, let's select this surface and create sketch and make a cut here. And by using this tool, we can define the clad thickness as 3 millimeters. And let's make clad, and let's select the solid. It's solid 2. And from here, let's select the orientation X. So we have here a clad on this flange by that way. Okay. If we come back to the 3D model, you can figure easily that after adding a clad to this flange, we may need to decrease the raised face diameter of this body flange, of this tube sheet. So we can come back to the tube sheet here from SEG3 and decrease the raised face, the inner diameter. Here, so the inner diameter we can increase it by 3 millimeters from both sides. And let's click on save, and let's click run the assembly. To modify the raised face or the inside diameter of the tube sheet to suit this change. And here we need to make one of those faces with a clad. Okay, so let's open the tube sheet from here. And on that side, okay, we will make a plan, sorry, we will make a working plan here and make a split to split this item to separate solids. And the first solid, we convert the material of this one to clad, so copper polished, and let's remove this one. So if you come back to the 3D model, you can figure that we make a clad on this tube sheet by that way. So that one will be like that. The same thing we will do it on the on that flange and the body flange. So let's open this one. Okay, and let's make a work plan here with 3 millimeters. Make split as the two solids. Define the first solid as another material, which is copper polished, for example. And let's make inside or internal clad on this flange. Sorry.
Ahmad, this all work we need to do in the inventor only, right? It's not with the SEG.
Yes, that's for the flanges, but on shell and head you can do that easily. Also on the flanges, some you have many different options for the facing and the clad location on the facing, so you can select create that easily by using the main tools of the Autodesk inventor. So now here, when we come back here, we can figure that the facing of the body flange, we need to decrease the facing of the raised face of the blind flange a little bit. So let's come back to the body flange here. And for the raised face inside diameter, we need to make it 5.7 and click on save. Let's click start simply. Okay, now you can figure that it's okay, you have a clearance here. So let's make a clad on this blind flange. So from here, let's make a work plan on 0 degree and make split. Okay, the same thing, we will select this solid and make it as copper polished like that. And let's make this plane invisible. Now we have this face with a clad like that. So easily we make this clad on the inside face of this one. By the same way, if you would like to make a clad on the channel or sorry, for the path partitions, you can make that by the same way. Here we have the model of the heat exchanger. Now let's check some points before proceeding with the drawing generation. Here for the bill of material, for example, if we open the bill of material table, you can figure that we have a list of items. Actually, we have 269 elements. Total on the list, 47 items. Here, for example, we have a spherical portion of the floating head. That's the dimensions of this spherical portion, the material weight and the weight. Here we have an ellipsoidal head on the bonnet. Okay, and here you can figure that the part name is indicated on this column, so you can know this item related for which item in SEG bill of material. For example, for this flange, okay, we have two identical items. It's NBS3 as a long welded neck flange with a RTJ facing with a class 300, and those are the other dimensions. You can detect that it's related to T1A and the T1B. Okay, and that's the material and the weight of each item. Okay. Here, the total item of the heat exchanger, which are around 3 tons. Okay, and you can export this bill of material in Excel format. So from here, you can export this bill of material if we select the desktop, for example, and that as home. Okay, if we go back to the desktop and sorry. Okay. I need to check this. Here for the external bill of material, if you would like to add some external attachments to the bill of material, like here in SEG model, it's not available to add spacers automatically from the application, but you can add it from SEG library. For example, here if you open, like what we did with the Crosby shackle, here if you open the SEG library, and from the accessories, you can find that you can get a spacer from here. And if you open this spacer, you can modify the spacer diameter, spacer length, all of that, and save it and include it to the 3D model in your project. One more thing, like if you would like, if we open this one, you can add eye bolts if you would like to add it in bill of material as to extract the tube bundle from the heat exchanger. You can add some standard circular washers or base plates, make J bolts, nuts, all of that U-bolt. You can add some external attachments to your model by using the external library of SEG, some standard hot rolled sections, tie rods, sealing rods, and some wires for lifting purpose or for transportation tightening purpose. Okay, now let's add some bolts for the flanges. So from here, let's select the blind flange, and from elements, let's add a stud bolt. One. And from here, let's select between ISO nuts with millimeters or UNC nuts. So from here, let's select 1 and 1/8 and define the material of the nuts as 7M. And for the bolts, it's like that. So let's take that one and bolt material. And for the nut spacing, let's measure the required spacing for nuts. So here that's 129.5, 1. And the length of the stud bolt, let's make it 190. Let's close this door and let's create this stud bolt. So we may need to increase the length of this stud bolt a little bit. So let's come back here and by the length. And let's select the flange 3, which is this flange, to add a stud bolt to tight the tube sheet with the next flange. So from here, let's select stud bolt. Okay, and let's click add. Let's select the size of the bolt, define the material and the stud material, and let's measure the required knot spacing, so from here to there. Okay, and the total is here. Save, and let's click start assembly. First, we will modify the first stud bolt. After that, we will generate the second set of stud bolts. Now we have the second set of stud bolts. Now we need to add another one right here. So let's select channel flange 2, which is connected to the bonnet, and let's add another stud. Okay. Find size, changes the material. Okay, the material, the knot spacing. So let's measure it from here, knot spacing. Here, length of the stud bolt, and let's create the assembly. Okay, now we have, I think we now close to finish the 3D model. We could proceed with the drawings after this step. But let's discuss some tables here. Here, after adding the nuts, you can figure that we have nuts here for the UNC bolts and stud bolts, now increased on the bill of material, different type of gaskets, saddle, ribs, nameplate, and ASME nameplate, and here another item. So now let's let's discuss some other tables like nozzle table. Here we have the nozzle table, include the nozzle tag, which is T1A, T1B, and the service of each nozzle as we defined, the size of each nozzle, the orientation, thickness, flange thickness, or flange class, sorry, flanger is the type, flange facing, if we have a blind, the blind facing rating and internal projection, external projection, weld style, and the fillet weld, dimension A, B, C. Okay, now if you would like to modify on this column and export some informations to your drawing, you can select it from select the required information and to export it to your drawing from here. A list of flanges, a list of fittings if you have a fitting, a nozzle orientation, that's the nozzle orientation, and material list like flange cover material, nut and bolt material, gasket material, a list of materials used in this project. Okay, now let's start creating the drawing. Before that, we can discuss some options for the units here. If you would like to change the format of the size of the nozzle from NBS, you can make it, and then you can make it NBS between brackets then, or between brackets NBS and the 10. You can select the suitable format which you would like to export in your drawing, in your tables. Sorry. And the same here for dimensions. If you would like to modify the dimensions, let's check one of those. For example, here if we select millimeter and inches between brackets and click save. Now, if you open the bill of material here, you can figure that the inside the radius of this spherical portion here, that is a value in millimeter, and between brackets in inches. The same for the thickness of this one here, that's the values between brackets. Okay, let's come back and change it and if you would like to make it in fraction option, by the way, you can select the fraction value. And if you click on save, now let's change it to make it inches and millimeter, for example. And if you click save, now if you open the bill of material, you can figure that the value here will be in inches with a fraction value. So it will be like that. You can figure that here, and that's the inside diameter in millimeters. So many different options to change the format of the dimension, and the same for the nozzle size. Now let's click on save, and let's proceed with drawing creation. So from here, let's click on create drawing, and from here, let's select the size of the drawing as A1. And from the active view, you can select the required views in your drawing. Here we have an elevation view, and let's add a right view, and let's make the spacing between them with 4 centimeters. So the spacing here defined it in centimeters. And for the orientation, here for the elevation view orientation, if you take a look to this model, so if we define the left view as the elevation view here, if you take a look here, so if you select the left view here for the elevation view, so that view will be the elevation view. Okay, so if you would like to make this view, which is the right view, so the blind flange will be on the right side and the head will be on the left hand side, so you will select the right view. And if you would like, for example, make it from top like that, so the elevation view will be like that. In our case, we will select the left view, that view, as the elevation view. So from here, let's select the left view and make it with hidden lines, so the hidden lines will appear. And if you would like make only the visible lines appear, you will select this option. And if you want to make it colored, you can select this option. Here, let's define the location of this view inside the drawing, and define the location of this one. Define the scale. Both values are roughly values. We will define it after creating the drawing to adjust the location of views inside the drawing. Here, let's select some tables like bill of material table, design data table. Let's select the nozzle table. By the way, you can add nozzle load table here, and I will inform you how we can do that. So from notes, you can add notes. If you would like to import it from an external Excel sheet, you can do that. And if you would like to edit, or so, for example, if you select this note, for example, you can make an edit on it like that. After that, you can accept it, or you can delete it, or add another note. Okay, for the welding styles, so let's select the suitable welding style. So we will select this style for the longitudinal welding lines, and that one for the circumference welding lines. Select that for the flange with with nozzle, okay, with a single V. Okay, let's remove this one, select that one for the nozzle collection. We haven't a nozzle with rebad, so you have a huge library for the nozzle weld details. You can select from them the required will detail in your case. And let's click on save. Now, if you would like to add a client document list, like process data sheet, mechanical data sheet, any other aspect, for example, so you can add those documents here on the client document list. The same from your side. If you will submit a mechanical calculation, you will submit a detailed drawing for nozzles, a detailed drawing for saddles, transportation drawing. So you can add a list of that, like transportation, number, and EWG number. You can add something like that. Mechanical calculation. Okay. Like that, so you can make a list from your documents that you will submit. Okay, now we have those tables here, and for the title block, we will create a drawing name like general arrangement, and here that's the document number. Okay, and for the revision table, let's select this row and make edit, so it's revision 0, issued for review. Okay, and for here, and if you would like to add some empty rows, yeah, you can do that. And for the design style, here this tab will give you the ability to increase the number of sheets they're drawing. For example, if you have huge equipment, and this equipment include a lot of information, and you would like to separate the bill of material on a separate drawing. So let's check that if we open a sample drawing here. For example, for this equipment, okay, like something like that, and you would like to separate the bill of material, and you would like to separate the bill of material here on a separate sheet, you can do that. Another one here, another sample. You have a lot of information on the first sheet, so you can separate the bill of material because it's a little bit huge. It will not come here on this drawing, so you can separate it on a separate sheet like that. So from here you can select the number of sheets that you would like, 1 sheet, 2 sheets, or 3 sheets, and move the table to another sheet. For example, the bill of material, you would like to move it to another sheet, so you can move it to a selected sheet from here after defining the number of sheets. Now let's select save. But before exporting that, let's save those information. I will inform you how you can add a nozzle load and create a nozzle load table in your drawing. Here for the nozzle load, for example, if you select the nozzle, and from nozzle load, you will be able to open the nozzle load form, and you can define the loads like, let's say something like that, and click on done. If you open the nozzle load table here, you can figure that you have loads for nozzle T1A. So easily, when you generate your drawing, if you open the generate form again and open the tables, when you select maximum allowable nozzle loads, it will appear in your drawing. Now let's create a drawing. Now we have the drawing creation. Here you can figure that the size of the drawing modified automatically, the nozzle table filled automatically. Now the bill of material is created and will be located on the right place on the drawing. Here that's the bill of material. The design data table. Here, as you can figure that we have because a lot of information, no enough space for the design data and the bill of material. So that may lead us to change the location of the bill of material table and change the column width for the rows to minimize the total height of the bill of material table. Now you can figure that the nodes, nozzle table, nozzle allowable, maximum allowable nozzle load, and here we have the weld details for nozzles will appear on the drawing like that. Okay, now we have the data on our model. We can move the bill of material manually from here to there, for example. Okay, and modify the column width. So we can increase the width of this row a little bit. So from the width, we can increase that to, let's say, 50 millimeters. And let's check that. Okay, it will minimize the height a little bit, so we can increase it maybe. I think it's okay now. Let's accept that and move the bill of material down here. Okay. Okay, we may need to change the location of those tables. Let's move those tables here. And the same maybe for the nodes. Let's move nodes here. And change the location of those views. We can change it manually, or we can change it from SEG itself. So if we come back here and from drawings view, we will change the location of the in X direction. So the X direction, which is the location from data point here. So it will be, let's say, on 34 centimeters from bottom, and keep the Y location as it is, or we can move it a little bit. Let's make it 33 and decrease the spacing between the two views. And let's click on create. Now the location of this, sorry, I changed the X direction, not the Y direction, sorry. So let's come back here for the drawing. And from here, it was 30 millimeters, and that was 38. Okay, and click create drawing. So now we will update the location of this vessel. We can move it a little bit up, or it's up to you. So we can increase the Y direction a little bit. So let's come back here. And for the Y direction, we can increase that 41 and click on create. So we increase it with 3 millimeters up, centimeters up, like that. Okay, now if you would like to make this view without color and make it with hidden lines, how we can do that? As we discussed, from this view, if you would like to generate a drawing from here, you can make this view without color. So we will remove the shaded type and make it with hidden lines. So let's select hidden lines from here and click on create drawing. So by that way, we can modify the style of lines, and by making the hidden lines available, visible like that way. Okay. Now let's add some balance and item definition for those items by using SEG tools. Here, from here, let's add a center line for this heat exchanger. So that's the center line here, and we have this center line there. And let's move this title a little bit down here, and the elevation the same. Let's move it a little bit here, and let's add some center lines for nozzles. Saddle or the nameplate to define the location of the nameplate, the second saddle, those nozzles, the lifting lug location, and it's the same. Now if we select the balloon, and by selecting nozzle tag number, when you select this nozzle, after selecting a nozzle tag number from here, you can add the nozzle tag as per your SEG tree, like that. So we have the nozzle tag like that, and the second nozzle, which is S1E. So by using this tool from SEG, which give you the ability to define the name of the element as per your definition on SEG 3. Now we have the name of elements. Sorry. Okay, this nozzle. Continue. That one. Like that. And the lifting lug here. Like that. Now, if you would like to add some other balloons to this balloon, like we have on the same location, we have this lifting lug, like adding it like that. We can do it by that way. To define the reference point, we can select the view from here and define the location of the datum point from the facing, for example, or from the flange here. It's up to you to define the datum line in your model. Okay, so let's select the location here for this nozzle. That one. The nameplate. And for this lifting lug and that one here. So we can move those balloons a little bit up here. And that one. Like that. So it's a reference to the datum line here. So if you would like to make this datum line invisible, you can make it like that by hide this datum line, and you can define it from the view by that way. So let's add this line as datum line. And let's clockwise like that. Increase this one and make this one as a center line like that. And let's click on finish. So that's the datum line of as a reference datum line. The same thing, we will do it at the bottom here. So for this saddle, the second saddle. Okay, and we can move those balloons. And if you would like to, it depends on how you will produce your drawing. The style of the dimensions, all of that, you can control it. If you would like to change the style of dimensions, change the reference point. For example, if you would like to add the dimension from the shell start point like that, you can do that easily by adding the dimension from here to there, like that. So that's the spacing of between elements. So that's the spacing between saddles to the shell end. So that's the shell end, like that. And the location of this nozzle from the facing of this flange, you can do what would you like to do. So here let's add the shell pins. So that's first shell pins. So let's add it like that. The second can, and that's can 3. So we can measure it from here to there. So we can it like can, and you can copy properties of here and there and modify the text like info. by that way you can generate your drawings. That's regarding to the GA. You can, if you...
hi, excuse me.
Yeah. Yes.
Hello, Hamid?
Yes, I'm hearing you.
Yeah, okay. I've got another meeting I've got to prepare for, so I'm going to have to leave now. But it's been a very interesting and informative session, thank you. So, Linson, can you just finish off the last bit, and then we'll speak later?
Yeah, sure, sir. Yeah.
Yeah. Okay, so, yeah, anyway, thanks very much. It's been very, very interesting, so I do appreciate your time.
Thank you for your valuable time. And by the way, you can go through our training videos for heat exchangers and vessels, and you will find a lot of information included on those tutorial videos. The session may be for 4 hours or 5 hours, so it will include a lot of information. You can take it as a guide if you would like to know how you generate an external item or something like that. Thank you for your valuable time, and I hope that we can cover some of your questions.
Yes, once I've discussed with Linson, we'll come back to you with any other sort of questions or queries we may have.
Okay, thank you so much.
All right, anyway, thanks very much.
Have a nice day.
Thanks.
Bye. Yeah, thanks.
Thank you, Deba, for your time.
Thank you. Hope the session was good. Okay, let me stop the recording.